Okay, so good morning, everyone. All right, so we are going to finish up with our content today, our acid-base balance stuff. Your practice exam for exam 3 is up. So hopefully this will be pretty quick. We're going to keep it to some big picture bullet points, but summary of where we are so far. Right, we've been talking about the kidneys. We know their functional unit is the nephron. Been talking about a lot of the kidney processes. So real big one is water balance, right? We're maintaining plasma volume and ultimately blood pressure by controlling how much water we reabsorb versus excrete as urine. At the same time as we're doing that, we're doing a lot of things with our solutes. So we're reabsorbing sodium. We're thinking about potassium as well. As we regulate our solute concentration, that also helps with our water balance. Okay, so our final topic was pH balance. Maintaining pH of the blood is another important role of the kidneys. Okay, so we talked briefly about this idea of acid-base balance. So we have a normal range for our blood. Normal pH is between 7.35 and 7.45. Lower than this is acidosis, means you have too many hydrogen ions. Higher than this is alkalosis. Okay, so we have been talking about this broad concept, and we have mentioned that one of the ways we can regulate the blood pH is with our lungs. So we're tying together our respiratory unit and our renal unit right here at the end. The reason we can do that is because carbon dioxide acts as a biological acid in your body. So we walked through how that works. Okay, this means that when we talk about acidosis and alkalosis, so pH disturbances in your blood, sometimes we're going to refer to them as respiratory acidosis or respiratory alkalosis, because they have to do with the fact that we are not breathing out enough carbon dioxide. We're breathing out too much carbon dioxide. So carbon dioxide is an acid. So if we are leaving too much in the blood because we're breathing too slowly, we'd have respiratory acidosis. If we're breathing too quickly and we're breathing off lots and lots of carbon dioxide, we'd actually be in respiratory alkalosis because we're not keeping enough acid in the blood. Yeah. So that's kind of where we were. We were talking about what goes in and out in terms of pH. We traced through why carbon dioxide works as an acid. And we mentioned that we can have other causes for changes to pH. So it's not just carbon dioxide. We're also going to be looking at the balance between carbon dioxide, oxidants and acid, protons or hydrogen ions, which are our technical definition of whether something is an acid or not. Lots of hydrogen ions means we have a low pH, means it's an acid. We have a balance with bicarbonate ions. That's that other thing on there, that HCO3 minus, that bicarbonate. Okay, so that balances out our acids. So when we lose bicarbonate ions, our acids kind of take over, causing acidosis. So if we have a cause of acidosis of low pH in your blood that's not because of your breathing, we refer to it as metabolic acidosis. And often this has to do with renal dysfunction. So that last bullet point means your kidneys aren't working right. Yeah. Alkalosis, same thing, just the opposite. So if we have metabolic alkalosis, that just means we have too high a pH due to something that's not your breathing. Okay, so something other than your carbon dioxide means you've lost protons, those hydrogen ions, or you've gained an awful lot of bicarbonate. Okay, so that's kind of where we left off. Okay, so to fix pH disturbances, we have 3 lines of defense. So 3 things we can do to fix it before this leads to really, really serious side effects. Okay, so the first is that we can buffer out our hydrogen ions. So a buffer is something that acts like a sponge, right? It can soak something up, or it can squeeze something out. right? So we're going to have chemical buffers in our blood that are able to limit changes in pH by binding on those hydrogen ions in situations where we have too many of them. But they can only limit the changes in pH. They can't fully reverse them. And eventually, those hydrogen ions that they found are going to have to go somewhere. Those buffers are going to end up basically full. Okay, so they can't totally reverse changes in pH. The only thing we can do if our pH keeps changing, keeps dropping, is add more buffer molecules to continue soaking that up. Respiratory compensation and renal compensation can both actually change the pH, so they can really reverse these changes. So our second line of defense is going to be to change how fast we're breathing. That's going to be respiratory compensation. So when we change how fast we're breathing, we change the amount of CO2 left in our blood, which is measured by that partial pressure of CO2, that PCO2. Okay. So if we change the speed with which we're breathing, we can change the PCO2, which means we can change pH ultimately. So this is considered a homeostatic regulatory mechanism for pH. Finally, renal compensation. So our kidneys can also reverse changes in pH. This is also homeostasis. So the ways they're going to do that is if our hydrogen concentration increases, so that's going to be acidosis, a drop in pH, more hydrogen ions, more acidic, low pH. Our kidneys are going to secrete hydrogen ions. So when we secrete, we take things from the blood, we put them back into the tubular fluid, they're going to get excreted as urine, right? So when we increase hydrogen ion secretion, this ultimately means that you're physically going to be removing those hydrogen ions from your body, bringing that pH back up. The other thing that we do at the same time in reaction to this increased hydrogen ion concentration, which is acidosis or low pH, is that we can increase our bicarbonate reabsorption and increase our bicarbonate ion synthesis. This means that we're going to essentially be making more buffer. Our bicarbonate is going to be our main chemical buffer, essentially, for hydrogen ions. Okay. The hydrogen ion concentration decreases by contrast. So fewer hydrogen ions is alkalosis, so basic pH. Okay. To fix that, we can decrease how many hydrogen ions we secrete. So they stay in your blood, right? So we're keeping that acid in the blood, dropping that pH back down into the normal range, hopefully, because we're not peeing them out, essentially. And we can decrease our bicarbonate ion reabsorption. So when we're not bringing as much bicarbonate into our blood, the bicarbonate won't bind as much hydrogen ions, so they're going to stay free circulating around in the plasma. Okay, so this is one of the main things that I want you to remember from today, right? So this is a big summary. The rest of this is kind of explaining how that works, okay? So for buffering, this is a quick defense against pH changes. Most important thing to remember that can buffer acidity in the blood, that can buffer hydrogen ions, that can regulate pH, is bicarbonate. So this is an extracellular fluid buffer, meaning it's in your plasma, in your extracellular fluid. So what happens is the bicarbonate grabs a hydrogen ion, and there we go. That hydrogen ion's no longer free and swimming around in the blood. Okay, so that's how it's buffering. We do have other buffers in the body. So we have some intracellular fluid buffers, including proteins. They'd also be able to bind hydrogen ions, and phosphates can also bind hydrogen ions. Okay, so this is our first quick defense against a sudden change in pH. But we want to actually fix our pH overall. The respiratory compensation is our second line of defense. We want to change our breathing in order to change pH. Okay, so this is going to take a couple minutes to have effect, right? You have to take a couple breaths in order to start to see these changes in gas exchange in the lungs and therefore in the contents of your plasma. Okay, but we're varying ventilation, so the movement of air in and out of your lungs, and therefore changing PCO2, partial pressure of CO2, because we're either allowing more or less time for that exchange. Okay, so if you increase your ventilation, so if you breathe faster, so more breaths per minute, this is going to decrease CO2, so decrease the partial pressure of CO2 in your plasma because you're breathing out more often. That's how you want to think of it. So if you increase ventilation, you're breathing off lots of CO2. So that CO2, its concentration, its partial pressure in your blood is going down. By contrast, if you breathe really slowly, so hypoventilation, you're not breathing off that CO2 as frequently. So you're increasing how much of it is staying in your plasma. So you'd see PCO2, that partial pressure of CO2, go up. Yeah. This is just a chart of how that works. We're not going to walk through it right now because fundamentally we just want to know that we can reverse these changes by changing breathing. If you like the flow charts, you can spend some time going through that image. Instead, we're going to talk about our third line of defense, the kidneys, the renal compensation. Okay, so this takes more time, hours to days, right? So this is a longer term thing. Buffering, seconds to minutes. Respiration, minutes-ish. Renal compensation, hours to days. Okay, so the way we're going to defend our pH, maintain our pH with our kidneys, as we saw on that summary slide, we can change how much hydrogen we get rid of. So the excretion of hydrogen ions, okay? And we can regulate excretion of bicarbonate as well, usually by changing how much we're reabsorbing. You don't reabsorb it, you're ultimately going to excrete it. Other thing we can do is we can actually make new bicarbonate. So we could make new bicarbonate in our kidneys if we need more of it to soak up more hydrogen ions, essentially. So we have outlined here what would happen if we increased acidity. So if the acidity of your blood plasma is increasing, that means you're experiencing a drop in pH, increase in free-floating hydrogen ions. Okay, so in response, you would want to secrete a bunch of hydrogen ions into the tubules so that you ultimately excrete them and get rid of them. You want to put more bicarbonate in your blood in order to buffer it out. So you're going to reabsorb more bicarbonate and you're going to make new bicarbonate. That's what synthesis means. Okay. Okay. So this happens, unsurprisingly, in specific places in the nephron. Okay. So in the proximal tubule, what we have happening is bicarbonate ion reabsorption. So in the proximal tubule, bicarbonate moves from the fluid back into your blood, into the peritubular capillaries, then circulating all around. Hydrogen ions get secreted. So hydrogen ions are moving from the blood into that tubular fluid in that proximal tubule. Under normal conditions, we're reabsorbing most of the filtered bicarbonate, not all of it like with glucose, but a fair amount, 80 to 90%. We're getting rid of a bunch of hydrogen ions. We know from before that we were reabsorbing sodium at the same time. Sodium drives a lot of processes. Okay. So in the distal tubule, we are also secreting hydrogen ions. So this is another place that we can get rid of hydrogen from our blood, move it back into the tubular fluid so that you excrete it out. What we're doing here is instead of reabsorbing bicarbonate, we're actually synthesizing new bicarbonate. So in the distal tubular collecting duct, we can make new bicarbonate ions and add them to the plasma, essentially creating more buffer for our blood, able to soak up more hydrogen ions. So those are the basics of what's happening. We do have pictures. Less important to thoroughly go through these. So we're going to go through this pretty quickly. So long as you understand the words on the slides, this is just another way to explain it if you want to look at this mechanism. So what we see here is, the proximal tubule. Okay. So in the proximal tubule, we know that we are able to secrete hydrogen ions. All right, so we see that secretion happening here. Right, so we're going from the cells of the lining back into the tubular fluid. Right, so we have those secreted hydrogen ions here. There are some bicarbonate ions here in the tubular fluid, so you're not going to have super acidic urine as a result of this. They do get buffered out in the tubular fluid as well. Okay. And we can see here that we are ultimately reabsorbing some bicarbonate. The way that we're doing that is through a little bit of a conversion process. So we take some bicarbonate ions that have been filtered into the nephron from the glomerulus, right? Just like everything in the plasma is other than the proteins, right? Ultimately, we converted that to carbonic acid, then to water and CO2. CO2 is what actually crosses into the cell itself. So that can dissolve or diffuse across the membrane because it's small and nonpolar. Right? This is our gas, ends up in the cell itself. We do another conversion process, have our carbonic acid again. Those dissociate back into the hydrogen ions in the bicarbonate. The hydrogen ions are getting pumped out, so that's going back to this secretion. But the bicarbonate ions that we now have in the cell are going to be moved towards our plasma into that peritubular fluid, ultimately into the peritubular capillaries. Okay, so this is hydrogen secretion and bicarbonate reabsorption. Oop. 3 minus reabsorption. Reabsorption. Okay. Okay, so that's what's going on in our proximal tubule. In our distal tubule and collecting duct, we have something similar but slightly different going on. Okay, this is actually in different cells that we've been talking about so far. So before, in all the previous processes, we were looking at the principal cells of our distal tubule and collecting duct. Now we're looking at something called an intercalated cell, but it's in the same location. Okay, so we again see hydrogen ion secretion. Okay, so that's still happening here. So I still have that secretion. Right. Now we're not pulling bicarbonate from the tubular fluid. What we're doing is pulling CO2 and H2O and water, right, that were potentially already in this cell, or we're in the form of carbon dioxide and water in the tubular fluid. And we're taking those two molecules and we're making new bicarbonate through that same conversion process, though, that we saw before. Okay. So we can reabsorb, but we can also generate new bicarbonate ions, essentially. So that's the difference that we see here. Now we do have the role of something called glutamine in this process. So glutamine is going to help us regulate the hydrogen ion secretion, the bicarbonate reabsorption, and the bicarbonate synthesis. Because if we have really severe acidosis, it helps us do that synthesis of new bicarbonate, essentially. Okay. Right. So when we're thinking about compensation overall, we're thinking about the balance of ions. Right. So in acidosis means we have too many of our acids, so usually too much CO2 or too many hydrogen ions themselves. Alkalosis, we have lots of bicarbonate, usually. Kidneys can regulate bicarbonate, lungs can regulate CO2. So when we say compensation, okay, compensation is going to be that fixing, that adjusting when we see a pH disturbance. Okay, so basically, if the lungs are messing up, kidneys can adjust the bicarbonate ions appropriately. So lungs, I forget what I just said. All right, if the lungs are malfunctioning, kidneys regulate. If the kidneys are malfunctioning, the lungs regulate. Okay, is what we're getting to here. All right. So when you're looking at these, are causes for respiratory acidosis, as I've been saying out loud, now written for you in the slides. Things like hypoventilation means you're keeping too much CO2. PCO2 goes up, increase in acidity. You would have to compensate for that with your kidneys because the problem is going on with your lungs, right? Basically, your hypoventilation is the problem. You're not going to fix the lungs with the lungs. That's what's going wrong. So you'd have respiratory acidosis with renal compensation. The way you'd compensate for that is secreting more hydrogen ions and increasing that bicarbonate reabsorption. We have respiratory alkalosis. So you're breathing too fast, breathing off too much CO2. You'd see decreased PCO2 in the blood, essentially decreased hydrogen ions. Again, if the problem is respiratory, the compensation is going to be renal. So you're going to just do the opposite. You want to keep more hydrogen in the blood. So you're going to decrease how much is secreted and therefore excreted. And you're going to not reabsorb as much bicarbonate because you don't want to buffer out the remaining acidity. In metabolic acidosis, problem is not your lungs. Therefore, you can start to fix some of it with your lungs potentially. Okay, so if the cause of acidosis, so high acidity, low pH, is hydrogen ions and not carbon dioxide due to weird breathing, okay, you can compensate first with the respiratory system, and then in the longer term, if the problem is not directly your kidneys, you can have your renal compensation kick in. So first thing that would happen overall, just like immediate, would be chemical buffering with whatever bicarbonate you have. Then your lungs are going to change your breathing. That's the respiratory compensation. So if you have metabolic acidosis, that means you have too much acidity in your blood. Carbon dioxide is an acid, so you'd increase your breathing to breathe off that acidity. So increasing that ventilation is going to decrease the CO2. Okay. Renal compensation here. So you are now going to try to solve the hydrogen ion part. So it didn't go black on there, just on my screen. Okay. So you are going to increase the secretion of those hydrogen ions. You want to urinate them out, excrete them out. And you're going to reabsorb some more bicarbonate to act as a buffer. And you're going to increase some synthesis of new bicarbonate. Okay. In metabolic alkalosis, you're just doing the reverse. Okay. So we have something going on that's not your lungs. So you're seeing a decrease in hydrogen ions, therefore an increase in pH. First fix is respiratory. So respiratory compensation for this is in order to bring that pH down, you want to have more CO2, our biological acid, our respiratory acid in the blood. So you're going to slow down your breathing. So you're going to decrease ventilation as a mechanism of respiratory compensation for this metabolic alkalosis. Then your kidneys kick in later, so long as they're not the problem. Okay, like if your digestive system is your problem or something. Okay? So we're going to decrease how many hydrogen ions we're secreting because we want to keep those hydrogen ions in the blood, drop that pH back down. You're going to decrease how much of that buffer is hanging around. So you're going to decrease our bicarbonate reabsorption, and you're going to decrease the synthesis of new bicarbonate. Okay. So we could pull this all together in order to determine what's going wrong in someone's system and how we're fixing for it by taking some samples, essentially, of the blood. Okay. So if we were to get a number for our arterial pH, the first thing we do to figure out what's going on with a pH disturbance is to determine whether we are outside our normal range or not. Okay. So our first step is to determine whether our pH is between 7.35 and 7.45. If it's not, we've got a problem. So if it's too low, acidosis. If it's too high, alkalosis. So we're going to run through our acidosis first. Okay. So our acidosis, our too low pH can have multiple causes, right? So we know that we could have a problem that has to do with our respiratory system and our breathing, or we can have problems with other systems in our body, possibly the kidneys, possibly things you ate, things like that, other disease processes. So first, we're going to check, how's our PCO2? How's the partial pressure of CO2 in the blood? Okay. So we're going to check, do we have a normal amount? So the normal amount of CO2 we're going to expect in our blood draw from the veins is 40 millimeters of mercury. That's our normal number, our normal partial pressure for veins. So if it's more, this means the problem is your lungs. Okay. So we can diagnose respiratory acidosis by finding a pH of less than 7.35 and a PCO2 of greater than 40. Okay. If we have respiratory acidosis, that means your kidneys are going to compensate for this. So we'd have renal compensation. Okay. Renal compensation is going to mean that to compensate for that additional CO2 that we have hanging around, we're going to want more bicarbonate. So we're reabsorbing more bicarbonate, we're synthesizing more bicarbonate. So our bicarbonate levels are going to be high. So our reference point for bicarbonate, we haven't mentioned before, but it's going to be 24. So 24 is kind of like your baseline bicarbonate concentration you'd expect. Okay. So we can run through the other side as well. So now that we know bicarbonate should be at 24, okay. If we find acidosis and our bicarbonate is less than 24, oh, okay. That means the problem is that we don't have enough bicarbonate, okay. Bicarbonate isn't regulated by the lungs, so that means this is metabolic acidosis. So metabolic acidosis coming from somewhere other than our lungs, okay? This means our lungs are able to compensate for it. So we're going to see respiratory compensation. So because we want to keep that 20-to-1 ratio of bicarbonate to carbon dioxide, we're now going to change our breathing, right? So we're going to change our breathing so that we can drop down that partial pressure of CO2. So we're going to breathe off more CO2, right, to adjust overall. So that's how this table works. So we could do the same thing for alkalosis. Okay? So alkalosis, too high a pH. Right? So too high a pH. The most direct reason for too high a pH would be too much bicarbonate. Okay? So too much bicarbonate would cause a high pH. Too much bicarbonate would come not from your lungs, possibly from your kidneys, possibly you ate a bunch of bicarbonate. Okay, so that would be metabolic alkalosis, in which case your lungs would compensate. Okay, so your lungs would compensate by increasing carbon dioxide, bringing that PCO2 up. So we could do that by breathing slower, keeping that carbon dioxide around longer. Okay. But we could have the reverse going on, right? So we could have alkalosis due to a low partial pressure of CO2, so lower than it should be. So this means we have like not enough acid in our blood. Okay, so this would be respiratory alkalosis because it has to do with CO2. So your kidneys would compensate by adjusting the bicarbonate. Okay, so the way I look at diagnosing these things myself, right, running through this, I would check your pH first, right? Check pH first, acidosis versus alkalosis. For me, the next easiest thing is to just figure out respiratory versus not. So for respiratory, you're going to have too high a CO2 if it's respiratory acidosis. You're going to have too low a CO2 if it's respiratory alkalosis. So my second step for you would be to check CO2 levels. Okay. And then the compensation is always going to be the reverse, right? So if you have respiratory acidosis or respiratory alkalosis, you're going to have renal compensation. Okay. Versus if you look at the CO2 levels and they're normal, that means you have metabolic alkalosis and you're going to have respiratory compensation. Okay. So that is my recommended process for looking at these levels. Right. But we do have our bicarbonate as well. So we could also look at those bicarbonate levels to assess. So questions at this point? Okay. So that's what we got. Our main takeaways. You want to know lungs and kidneys are regulating your blood pH. They're doing this through regulating carbon dioxide levels when we're thinking about the lungs. Kidneys are doing hydrogen ions and bicarbonate. You want to know which direction those hydrogen ions and bicarbonate ions are going. And you want to be able to tell me whether something is, for example, respiratory acidosis with renal compensation or any one of these other choices. Plus that slide about the overall compensation steps. Okay. And I'll put in an outline specifically the facts I expect you to know, but that's kind of big picture of where we want to be. And that's what we got.